is to continue this discussion of non-commutative geometry for a while, talk about Hochschild invariance and pairing on Hochschild homology introduced by Sheel Ganatra, and then we'll develop as many applications to Fukaya categories as we have time. So this part 3 is partly work in progress and so on. OK, so let me remind you what Hochschild invariants are. OK, so we'll start with a pair of a category or algebra and a bimodule over it. And by category, I mean DG or A infinity category always. And to such a pair, we can associate a group called HH lower star of CB, HH upper star of CB. HH lower star is called the Hochschild homology, and HH upper star we call cohomology. And on the chain level, the Hochschild homology is some sort of derived tensor product in the category of bimodules. So what I mean is this is the cohomology of this thing. With the diagonal bimodule in C, Hochschild cohomology is some sort of R-hom. From the diagonal to B, and there's some algebraic invariance of this pair. And out of this sort of construction, I can get invariance of the category C itself. I don't need to talk about a different bimodule. I could just think of Hochschild homology of the category C to be Hochschild homology with coefficients in the diagonal bimodule. And similarly, Hochschild cohomology. OK, so we have Hochschild homology and cohomology. These have various algebraic structures, as you might imagine, from homology and cohomology theories. In fact, it's quite rich. Just to give you a sprinkling of them, this has a ring, Lie algebra structure. I mean, more generally, you'd say it's a Gerstenhaber algebra. This has some sort of module structure. Hochschild homology. Homology is a module over cohomology. It's some sort of Gerstenhaber module over cohomology, and it has some sort of BV operator. So I won't go into the full detail of that, but maybe I'll just tell you what the commutative analog is when you have a variety over C. So if I was working with perfect complexes on, let's say variety over C, we have HKR type isomorphisms between the Hochschild homology of perfect complexes and the cohomology of the sheaf of differential forms, and between Hochschild cohomology of perfect complexes and the cohomology of polyvector fields. OK, and after some sort of suitable correction, so there's something you might write down as a naive HKR map. This was introduced by Hochschild, Kostan, and Rosenberg. There's sort of a well-known story about globalizing it to a general variety. You have to kind of fix this map by some characteristic class, some square root of Todd. After some suitable correction, HKR intertwines lots of algebraic structure on both sides. Okay, I'm just going to, it's expected to intertwine everything. I don't think that's in the literature. But let me just say on this side we have sort of what you might call a calculus structure. Okay, so I'll just say that in words. you have forms, you have vector fields, you can contract forms against, you can contract forms against vector fields, you can take Lie derivatives, things like that. You can take brackets of vector fields, etc. And over here we have what might be called the non-commutative calculus of a DG category. And that includes some of the structures I've described here. OK, so there's sort of a very long list of names I should attach here. And I'll attempt to attach a few of them, but maybe an incomplete list. So for instance, Kontsevich and Soibelman and Tamarkin and Segan write about non-commutative calculus quite extensively. And maybe I should say that this notion that HKR needs to be corrected probably was first introduced by Kontsevich. Calderaro suggested some things involving these algebraic structures. Kalak, Rossi, and Vandenberg. Markarian, Ramadas. OK, there are lots of people whose names I'm probably missing, but this is just to give you, I think the main punchline here is we can think of these invariants as knowing something about calculus on this non-commutative space C. That's really all I want to say. And maybe one thing I want to say is we're going to focus on one such structure. OK, so one such structure in calculus. So for example, there's an integration pairing called the Mukai pairing. So when x is proper, there's an integration pairing on the cohomology of differential forms. That's simply up to some constant factor wedges a pair of forms and integrates. OK, and so this philosophy that OK, so this is some sort of bit of calculus. There's some philosophy that it should come from something purely on the category. OK, so Shklyarov introduced a pairing defined completely in terms of the category on the Hochschild homology of any proper category. That corresponds to the fact that you can only integrate like this when your variety was proper. OK. OK, so let me call this pairing bracket SHK. And Markarian and Ramadas proved that these two pairings are compatible or are intertwined under this corrected HKR map. OK, so what is this pairing? That's what I want to really talk about. OK, so I'll start with some general stuff. So if I have B a proper bimodule over a category C, remember a proper bimodule has finite dimensional cohomology. Okay, so a proper bimodule over C is the same as a functor from C times C op to chain complexes, but the properness condition means you map to chain complexes with finite cohomology. Okay. OK, so I'll call, so this is the functor that takes a pair of objects and looks at the chain complex, which is B of the pair of objects. Let me call this functor phi sub B, just to separate between the functor and bimodule point of view. Okay, so the basic fact about Hochschild homology is it's functorial with respect to functors. Okay, so I can just look at push forward on Hochschild homology. Okay, so I get this induces a map phi b lower star from the Hochschild homology of C. Okay, so now I was thinking about this as a bilinear functor. Let me instead think of it as a functor from the tensor product. Okay, so now let me not worry about, let me just say C is dg. Okay, so I get a push forward functor from the Hochschild homology of C tensor C op to the Hochschild homology of perf k. Okay, but Hochschild homology is a Morita invariant. So Hochschild homology of perf k is Hochschild homology of k, which is k. Okay. On the other hand, the Hochschild homology of C tensor C op, well, Hochschild homology obeys a Kunith formula. So this is the tensor product of Hochschild homologies. Okay, and Hochschild homology doesn't really care if you look at the opposite of a category. So there's some op invariance property of Hochschild homology. So this is just Hochschild homology of C. Okay, so this is op invariance. And so this is just isomorphic to Hochschild homology of C tensor squared. And so I get an induced map called pairing sub B. Yep?
How do you make this work when C is A infinity?
Yeah, so when C is A infinity, look at a recent paper of Nick Sheridan's. When C is A infinity, what you should think about is how a bilinear functor induces a push forward from the tensor product of Hochschild homologies directly. Okay, so I won't say, I mean.
So class of B is just a bimodule structure map?
That's right.
Yes. I mean, this idea that there's something complicated about tensor products of infinity categories is misguided, right? What happens is that, it's difficult to the same extent that the Eilenberg-Zilber theorems or something.
That's right.
Topology, right? Nobody would say, "Oh my God, I have to use the Eilenberg-Zilber theorem. Let me not do it."
Sure.
Okay. So you can write down a formula for tensor product of A infinity. It's not pretty.
Is it just inserting bar stuff?
I don't know. I mean, the thing is, it's based on diagonal approximations in associahedra.
But you can skip all of that entirely. I mean, I guess.
Just like that is, or you can replace it by dg and do a tensor product. Replacing by dg is just like saying,
right.
Oh, in singular homology, I'm so scared I'm going to use cubical synthesis.
Right, but let me.
Then everything
right.
works well.
I want to say one thing. You can just bypass that entirely.
Yes.
And you can just think about bilinear functors and their induced maps on tensor products of Hochschild homologies, and that but I think is a clean way of point of view.
The bypassing thing happens to be canonical, so you have easier to write it down. But the other thing is canonical after homotopy, so it didn't solve a problem that you had, just pedagogically. Now that I wasted some time, yes?
I have an unrelated question.
Yes.
So, okay, I assume since you said everything implies lots of algebraic structure, that maybe the cup product on the right is seen on the left on Hochschild homology of X.
No, I don't think it is.
Okay.
Not allowed to, because there are derived equivalent Calabi-Yaos with different ring structures.
Okay. So then,
Really
if
not
the answer
allowed
were,
to.
if
Yeah.
the answer were yes, I was going to ask why are we finding the pairing and not just the integration map?
Yeah, no, absolutely. So.
More questions?
Yeah. So. Maybe it's worth saying that this passage to a category is a little bit lossy. So it's sort of you keep a lot, but you don't keep everything. So, but you can still retain a surprising amount of information. Okay, so there's this pairing for any bimodule B that's proper. Okay, so if the category C is proper, then by definition that means its diagonal bimodule is proper. Okay, so that's the bimodule you get just by looking at Hom as a bilinear functor. Okay, and you define the Shklarov pairing to be the pairing associated to this canonical bimodule. Okay, so I think the power of this structure comes from the following proposition, which tells you that if you knew that C was smooth, then you actually know quite a bit more about this pairing. Okay, so there's a proposition due to Shklarov which says that if C is in fact also smooth, so C was already proper so that there's a pairing. If C is also smooth, then well, first of all, the Hochschild homology of C is finite dimensional. That's not due to Shklarov. That's maybe more straightforward to see. And this pairing is actually non-degenerate.
Symmetry.
If C is weakly Calabi-Yau, it's symmetric or something. Okay. Otherwise, it's not. So, I mean, the failure of symmetry, I think, lies in this identification of Hochschild homology of C up with C, and there's some. You're worried that that thing is symmetric for a non-Calabi. Yeah.
Right?
Yes.
Just to make sure,
Yep.
since here you said, you talk about his, or, I don't know, that person's pairing, and then you talk about the NC pairing.
Oh yeah.
So that-
Sorry, this is Shkarov's pairing.
Okay, I thought so, but I just wanted to make sure. So that pairing is introduced for a general proper bimodule, and then you make the specialization to define it for the category. Okay,
That's right.
I just wasn't sure.
Great, thanks. Okay. Why is it that it isn't symmetric? Well, I mean, there are these factors of I that depend on.
Well, I mean,
Yeah.
the pair, it's but still, there's something else.
Well, the harm is not symmetric. The same reason that the
So somewhere in this identification, something's gone wrong, because there is the pairing, the integration pairing seems to be symmetric, but this, when we're not doing that, right, there's also something extra there.
Yeah.
When you said absolute value of alpha
Yes. Degree of alpha.
in
Degree of alpha, that's a good question. Do I mean cohomology or some mixed thing? I don't actually remember off the top of my head. Nick, do you happen to remember offhand? That's kind of not the focus of my talk, so I didn't sort of like think about it very carefully. But
so maybe this is a bad question, but is there a way to say in 2 words why it's non-degenerate?
I'm going to prove it. Okay. So here's a sketch of proof. All right. So the starting point is, again, I'll do something general for any bimodule, and then I'll specialize to the diagonal bimodule. Okay. Another question? By the apparent symmetry.
just
I copied this from a formula somewhere.
yes,
You know,
but
it's-
where-
yeah.
where- Okay, well, actually, there's a question. Actually, HKR tilde is not a harmless thing.
It's not a harmless thing. That's
So
right.
let's not obsess with
That's that. It's more complicated. Of course, you have to do like take the square root of Todd, blah blah blah. I mean, so yeah.
So that's where this guy here with the eyes is kind of, if your eyesight is bad, it could be symmetric, but after you if you compose it with HKR, you will get the. Okay.
Okay, so the starting point is that for any perfect bimodule, there's actually a copairing. Okay, so you can associate a copairing, which I'll call the Chern character of that bimodule in the Hochschild homology of C tensor C. I'm now going to start forgetting about ops. Okay, via the following. So a perfect bimodule. So there's a functor. Anytime you have an object in a category, there's a functor from the category with one object to the category that sends the object, sorry, the one object to the object you're interested in. Okay, so this is I'll call this f sub b. And the Chern, oh, sorry, this is p, f sub p. And the Chern character of p is the push forward of the generator 1. So there's a push forward map from Hochschild homologies. And now Hochschild homology of perf of something is Hochschild homology of the tensor product because of Morita invariance. Okay, so okay, and this pairing and copairing satisfy an important relation, which you might call the snake relation. Okay, and you can say it as follows. So let's say B is proper and P is perfect. Okay, then there's a map. And there's a map from Hochschild homology to the triple tensor product of Hochschild homology to Hochschild homology again. Okay, which does the following thing. First, you introduce 2 copies of Hochschild homology. You act by the identity on this copy, and you introduce 2 copies via tensoring with Chern of P. Okay, so there's a map K in by Chern of P. Okay, and then you contract the bottom 2. Okay, by looking at the pairing with respect to B. Okay, so this gives you a map from Hochschild homology to Hochschild homology, and the snake relation says that this coincides with the following map.
What's the map downstairs?
What do you mean downstairs? This is the identity.
Oh, okay.
That's right. And now, what do I want to say? Maybe I should have written this up here. And that goes to K. Okay, so this is the identity. So I introduce 2 factors to the left and then contract the 2 factors on the right. And it looks like this snake. Okay, and this coincides with what? There's a single map I can write down from Hochschild homology to Hochschild homology, this composition. And what is it? It's the, so I can take the functor oh no, I want the other way. Okay, so I can take the functor. So each bimodule is a functor from perf C to perf C. Well, let me claim that. Okay.
One goes from perf to 1, and the other goes from perf to 1.
The composition goes from perf to perf.
So
Yeah.
yes, when would be good? Yeah, exactly. It's pure spelling.
Yeah.
I know. I think you should spell out each.
Okay.
Composing with B.
Mm-hmm. So composing with B,
B is proper, that's all we know. So
B is
it goes
proper,
from
so it
perf
just,
to mod.
it goes from perf to mod. It goes from perf to prop, actually. It goes from perf.
Prop, sorry.
Yeah, so B, composing with B, goes from perf C to what I'll call prop C. This is proper modules. And because B is proper. And composing with P goes from proper modules of C to perfect modules. Okay, and this is the composition. It's a map from perf C to perf C. Okay, and therefore it induces a map on Hochschild homologies of perf C, which is just Hochschild homology of C. Okay.
So composition left to right?
Yeah, I'm composing left to right. So this is apply B, then P. That's right. So it's P composed with B, but the way I'm writing it is in terms of this convolution product. So, okay, so there's a snake relation, and this tells us everything. I'm going to claim this proves the proposition very quickly. Okay, so let's do that. Now, if C is smooth and proper, apply the snake relation with B equals P equals the diagonal bimodule. Okay. So if we write, so now on one hand, the composition okay, this composition map that's at the very bottom is the identity map. Okay, right, and at the top I have this sort of churn character followed by pairing. Okay, so this implies that if if I write the churn character of this diagonal bimodule as some sum of elements, this is always a finite sum because of how Hochschild homology is defined. It's some sort of finite sums. So churn character of the diagonal bimodule is this. That this implies that if I apply identity, so this implies that for any v in Hochschild homology, the identity applied to v equals this expression. I take the churn character and I contract this element beta I with v, and I take this sum, and that equals v. Okay. Okay. So of course, what does this imply? This implies that alpha I is a finite basis for Hochschild homology, and it also implies that beta I v is not 0 for some beta I if v was not 0, because some of them equals v, right? So that,
Maybe not basic, but generated.
yeah, that's, well, I mean, I'm working over a field, so this is a,
But you could.
sorry, what? Yeah, okay, fine, sorry, okay. They generate, yeah. Does it generalize to rings? I think everything I said so far didn't involve really working over a field. I mean, but I have to always think when I. So
I mean, it depends what you mean by, you have to define a non-degenerate pairing as sometimes it induces something that induces a quasi-isomorphism to the dual.
yeah, I mean, you have
You're
to
working over a ring Hochschild homology could have torsion, so
right,
you know.
modulo what you mean by non-degenerate pairing, as we already know from Poincare duality. Right. Okay. I mean, there's some usual, maybe don't want to go into it, but okay. So this is the non-degeneracy desired. Okay, so all of this really just involved some basic functoriality and some properties of properness and perfectness and things like that. Any questions about this, first of all?
Yes.
Yes.
So, I mean, you formulated the snake lemma on Hochschild homology level, but is there a underlying functor level thing?
Yeah.
When I say just go from C to C tempo, C tempo, C.
That's right. That's right. I mean, I think it's easier to state in terms of perf C, but yes. There's a snake lemma on the level of so you introduce these two things and you contract those two things, and yeah, that's.
So there is
This one's actually very trivial. I mean, there's almost nothing to say. If I take a perfect module and I tensor it with a perfect bimodule over K, I get an element here. Okay, and now if I contract, yes, there absolutely is.
I think that morally a way to paraphrase this lemma is to say that if you have a pair of adjoint functors that are proper and smooth, then they induce adjoint maps, and if you unpack that, then it should give you everything.
I think that's reasonable.
So in particular, I could use some other invariant, say periodic cyclic homology.
Yeah, no, this works perfectly well with periodic cyclic homology. There's a pairing on that level too. It's called the higher residue pairing. Shklarov also introduced a version of this, and Nick also wrote a version for the A infinity case.
What are the
The K theoretic implications.
So it's false on K. The pairing is perfect.
Well, it has to be, right? Otherwise, K-theory would be boring, but
It's true in a sense on perfect module categories, so it's a little confusing to me.
Oh yeah, it's maybe it's true on the level of categories, but it's false on the level of K theory. So even for perfect varieties,
I mean, there's a pairing.
there's a pairing, but it's not.
There's a pairing and a co-pairing, and they satisfy some property, but
it's a question of the failure of Kuhne.
yes,
Yeah.
I think that's absolutely I think that's absolutely right.
Still thinking about the ring thing. Of course, you can define a perfect pairing over ring. Just say that the determinant of the matrix is immutable.
Mm-hmm.
And I'm wondering whether you might be wanting to use this work like Nick's when he works over something that rings rather than years.
I agree. It would be interesting to think about it carefully over a ring, for reasons like that. But maybe let me move in a different direction right now. But okay, so we have all of this. Maybe it's worth pointing out that the pairing is developed as sufficiently formal that actually there are a number of extensions you can already start to think about, and there are already a number that are relevant to geometry. Okay. Okay. The first is a very mild extension. I mean, okay. So the first, instead of looking at the Hom pairing, so if you have any proper pairing between not C in itself, but any pair of categories. Okay. You get a pairing on Hochschild homology. On the Hochschild homologies of these categories. Okay. There's and this is relevant because okay, C or one of these categories may not actually itself be proper. Okay. So here's an example that arises in geometry, let's take C to be the wrapped category of X. Okay, it's non-proper. Take D to be the Fukaya category of compact Lagrangians in X. Okay. Oops. Then if you, okay, so the Fukaya category of compact Lagrangians is a subcategory of the wrapped category. But if you look at the Hom pairing from the wrapped category of X, tensor the Fukaya category. To chain complexes, if you have a non-compact Lagrangian and a compact Lagrangian, their Floer homology is always finite rank. Okay? So this pairing actually lands in perf K. Right? So there's a pairing between the Hochschild homologies of these two categories, which can be profitably or meaningfully studied. Okay, so or if you like algebraic geometry, you might want to look at the pairing between coherent sheaves on X and perfect complexes on X with compact support. Just look at the usual X pairing that also lands in perfect complexes. Okay, same situation. Sorry, what?
These are not smooth and proper.
Yeah, so that's right. So well, this is smooth. That's proper. Okay. So an interesting thing about it is sometimes a smooth category and a proper category have a perfect pairing anyway. Okay, even though a given one of them isn't smooth or proper.
Can you still prove it even though this one is smooth?
Sorry, what?
Can you still prove it?
Under some hypotheses. I mean,
True what?
this pairing is perfect.
Or non-degenerate?
Yes, non-degenerate. Let me. Okay, I can say something like very simple hypotheses. Okay, which is that this is an instance. There's a much simpler version of this called causal duality. Okay, so this is. Let's see. So if A is a smooth DGA, which has a causal dual, A check. Okay, so then this causal dual is proper. Okay, so the prototypical example is an example I mentioned last time. Chains in the base loop spaces has a causal dual, co-chains on M. If at least if pi1 is 0, this is a faithful duality. Okay, and smoothness gets turned into properness and vice versa. And you can actually study you can actually say that there's a perfect pairing. Okay. There's a perfect pairing. A So there's always a pairing, and more, even when there's no causal duality, it's perfect when there's causal duality. So, okay, so I mean, under some limited I think there actually it's an interesting question about in what level of generality you can say this, and I think we would learn a lot if we knew the right level of generality to say it. Okay, the other thing you can do is you can actually twist the story. Okay, and well. Okay, so you can twist by a bimodule. What do I mean by that? Well, if you think about this Mukai pairing, you could just as easily write an integration pairing between forms twisted by a line bundle and forms twisted by the inverse line bundle to K. Okay. So in the commutative setting, that's what I want to generalize. So the proposition is that if let's see, if C is a proper category and B an invertible bimodule, on C, then there's a pairing which I'll call the Shklarov pairing twisted by B from the Hochschild homology with coefficients in C, tensor the Hochschild homology with coefficients with Hochschild homology with coefficients in B, tensor Hochschild homology with coefficients in B inverse to K. Okay, if C is smooth, this is a perfect pairing, as in the untwisted case. Okay, so I mean, a lot of the proof.
Did you
Yep.
actually say what? Did you say what Hochschild homology with coefficients?
Yes, I did. But well, I can indicate how to construct this pairing, or I could skip it. Okay. So what we need to do is at the end of the day, as we saw last time, you need to produce a map from the Hochschild homology of C tensor C op in the previous case, but now it's the Hochschild homology with coefficients. This is just the tensor product of Hochschild homologies. I'm just applying Kunith, right? Okay, to the Hochschild homology of perf K. All right, how do you do this? Well, Hochschild homology with coefficients isn't quite as functorial as Hochschild homology is. Okay, so you have to grapple with that fact. Okay, so if you wanted to get a map from Hochschild homology of C with coefficients in B to Hochschild homology, actually, let me just use A with coefficients in B, I'm just going to use all different letters. If you want to get a map from Hochschild homology of AQ to Hochschild homology of, AP to Hochschild homology of DQ, you need two pieces of information. You need the functor from A to D, as before. Okay, but you also need a morphism of AA bimodules between P and the pulled back bimodule F upper star of Q. Okay, so this is so we have to produce that second piece of data. Okay, and I'll attempt to say this somewhat quickly. In our case, A is C tensor C op, and P is B tensor B inverse op. Okay, and D is perf K, and Q is the sort of the diagonal bimodule. Okay, so we have the functor. That's as before. Okay, what we need is a map of AA bimodules, okay, where A equals C tensor C op between what? Between B tensor B inverse op to the pullback of the diagonal bimodule. Okay, so this, well, it looks a little messy, but you can just unpack all of this. Okay, so first of all, an AA bimodule is a, so this is, an AA bimodule is a C tensor C op, tensor C tensor C op module. Okay, so I have to grapple with 4 multiplications by C. So let me number them. 1, 2, 3, 4. Okay, and how do these algebras or categories or whatever act on this tensor product of bimodules? I think the action is something like this: 2, 1, 4, 3. Okay, left, right, left, right. Now, what is this funny-looking bimodule? You can actually just compute, check that it's the following. It's Hom and chain complexes from the diagonal bimodule to the diagonal bimodule with 4 independent inputs. Okay. So I'll just write that as Hom C delta with a different bimodule structure. And what did I think it was? 1, 3, 2, 4. Okay, so this is just some explicit piece of data you need to produce. And actually, it's very easy to produce it because this map that we want, eta, exercise eta is adjoint to a map. Like this. I can just move one of the delta, the diagonal bimodule factors to the other side, take a tensor product like this. But this is just B tensor B inverse, which is isomorphic to C by invertibility. Okay, so I just choose the isomorphism. There's my map. Yes?
Is there a way of writing down the pairing graphically?
Yeah. No. I mean, it becomes a little bit. Yeah. So there's a perfectly nice way to write them graphically for the non-twisted case. I'm still like, there's this.
I second this.
I mean, like, put things here if you're contracting.
Yeah, I mean, we're actually
Okay, I like to,
right. Exactly.
I like those like a
Sorry, what? Sorry.
like Hoxha's homology of B tensor with itself.
Yeah. And assuming that the chain roots are finite dimensional.
Oh, okay. This thing. Yes.
You
Yes.
know how to do it.
Yeah. Okay. It's like, yes. Okay. Fine. We can. Okay. So we have the following thing. If alpha and beta are Hochschild chains, okay, so I think about alpha as like some circle of morphisms, and beta as some other circle of morphisms, and each of them have a distinguished start point. Okay, and that's kind of the only distinguished point in this chain. Is where the chain starts. Okay, then the pairing is something like some sines times some sort of trace. Okay, some sum of traces of something like this. So there's an operator which behaves like follows.
CR being like graded trace or super trace?
Yeah, graded trace. That's right. Okay, so there's an operator which I'll describe as something like this. Okay, there's an operator that takes an input contracts on both sides some of the input with some sequence of elements containing the start point of alpha and some sequence of elements not containing the start point of beta, and then contracts once more with a sequence of elements containing the start point of beta and not containing the start point of alpha. This defines some linear operator. Okay. Okay, so there are formulas like this, maybe I should say. By Shklarov and Sheridan in the A infinity case. And what I'm writing down is some version of that for A infinity categories. So mu's are my A infinity multiplications.
So what if this is an operator acting on some vector space?
Acting on some vector space.
What does it say?
Some home space.
Some Hom space of an object.
Okay.
But in practice, there will be several home spaces depending on how you break down the Hochschild chain.
Yeah, it's
How you break it open.
that's right. So it's whatever Hom space that is between these two objects. So I choose to break up my Hochschild chain in some way. I sort of choose a cut. I get a pair of objects here, and I take an operator on that Hom space. I take its supertrace.
But why is the input vector space and the output vector space the same?
Because of the way I broke things up. So these live on a circle, like the beta morphisms live on a circle. So that this boundary component and that boundary component line up.
Oh, that's beta.
Yeah, that's beta, and this is alpha. So that's why the input and outputs are the same. Other questions about so for the last while I was planning to talk about why we might care about this sort of stuff if you care about Fukaya categories. Okay. So I'll be impressionistic, and I won't actually define the Fukaya category or carefully write down any of the operations, but I'll just indicate what's going on formally and how these pairings actually start arising. Okay, so we start with maybe a compact symplectic manifold, and I'll assume that we can associate some version of its Fukaya category over some field. I'm not, yes?
Should have asked this like 5 minutes.
Oh, that's fine.
If you replace B by something where the sort of trace splits, like the line bundle with the vector one, these results still hold?
I didn't think about it. Maybe. I'm not really sure.
I think you would need, instead of B and B inverse, you would have 2 adjoint functors.
Yes, actually, this completely goes through with 2 adjoint functors. So instead of B and B inverse, if you have an adjoint pair, all you really need is the unit and co-unit of the. So here you need some sort of like co-unit of a junction. There's something like that, and then the Chern character is some sort of the other way. Okay. So I think yes. Okay, great. All right. So let's say we have some Fukaya category. We might be interested in computing its Hochschild invariants, or understanding them in some way. And for that, we use open-closed maps. Okay, so for a compact symplectic manifold, we have maps from the Hochschild homology of the Fukaya category, the quantum cohomology. This is called OC, or the open-closed map. And there's a map CO to Hochschild cohomology of the Fukaya category. I'm going to kind of disregard this map mostly because I don't have enough time to talk about it. But maybe it's worth saying that there's a funny thing going on, which is that, okay, we might expect these maps to be isomorphisms in nice cases, which would imply that Hochschild homology and Hochschild cohomology are isomorphic, which isn't true for a random category. Okay, so maybe I just want to so the fact one expects, one in fact expects an isomorphism Hochschild homology of the Fukaya category is isomorphic to Hochschild cohomology, and this has to do with some sort of Calabi-Yau structure. On the Fukaya category, the mirror of this, the point is the mirror of a compact symplectic manifold is always calabi-Yau. And in particular, its polyvector fields are isomorphic to the cohomology of its differential forms via contracting with a choice of holomorphic volume form. Okay. Right?
You're saying one only expects that in the calabi-Yau case?
One only expects that when the mirror is calabi-Yau.
Okay.
So I'm not thinking about X itself being calabi-Yau. I'm thinking about its mirror being calabi-Yau. Okay. And compact Fukaya categories, when they have mirrors, they're always calabi-Yau. That's.
And are you defining the map OC or?
I was hoping to avoid it, but I could define it. I mean,
What does it mean conceptually, though?
what does it mean? So I would say, okay, so I would say, we have these HKR maps on the other side that compare Hochschild homology of perfect complexes to some meaningful cohomological invariant.
Yes.
And this is a version of that in the A model.
Is there a geometric picture?
Okay, so I can draw a geometric picture. Why not? I've been avoiding writing down holomorphic disks this entire series, which maybe is blasphemous. Okay, so these open-closed maps come from studying disks with some boundary condition on Lagrangians, some mark points on these Lagrangians, and so on, and some interior mark point constrained to lie on some interior cycle. Okay. So you study holomorphic disks like this, and if you think about what are inputs and what are outputs, you get some operations. Beta is an ambient cycle.
So it's a mark point in the interior?
Yeah, it's a mark point in the interior of the disk that goes to some point in the interior of the manifold, and you constrain it to lie on some homology cycle.
Okay.
And as you vary your homology cycle, you get a different count, and for any collection of boundary inputs, and this put together in some way gives you a map. Maybe what I want to say is there's also, if you have a symplectomorphism from X to itself, there's also a group HF of phi, okay, which is called the fixed point Floer cohomology. So HF of identity is what I was calling quantum cohomology. And HF of phi is some generalization, some chain complex built out of fixed points of this symplectomorphism, and a map OC twisted by phi from the Hochschild homology of the Fukaya category with coefficients in the bimodule phi to the fixed point Floer cohomology. Okay, so remember that what is this? I have to specify a bimodule. I just gave you a symplectomorphism. What I mean by this is I look at the bimodule hom phi dash dash. Okay, so that's a perfectly reasonable bimodule. I can take Hochschild homology with coefficients in it. Okay, so this is called the graph of phi bimodule. Okay, so maybe I'll start by stating, now how these pairings relate to this structure. So we have a pairing on quantum cohomology. Just given by classical cut product and integration. Okay, so let me call that. And we have a pairing between the fixed point Floer cohomology of phi and the fixed point Floer cohomology of phi inverse. Generalizing this pairing. Okay, so I'll call that some sort of phi twisted pairing. Okay. And so all relations about automatic generation and computing open-close maps and so on boil down to the following relationship between this pairing and the Shklarov pairings. Okay, so that I think is kind of the key point, and then you can play with the algebra and extract various consequences. Okay, so the first theorem is joint with Peretz and Sheridan, and I understand Abu Zaid, Fukaya, Ota Ono also have a version of it. And it just says that OC intertwines the Shklarov pairing and the sort of cohomology pairing, okay, up to some overall sign. Okay, by this I mean if I take the Shklarov pairing of two Hochschild chains, this is the cohomology pairing of their OC maps. Okay, and once you know what the twisted Shklarov pairing is, there's a very mild generalization of that, which is that the twisted OC map intertwines the twisted, maybe I should say the pair, the twisted OC map by phi and by phi inverse. They intertwine the twisted Shklarov pairing with the pairing which I called ordinary parentheses sub phi. Okay, so why is this helpful for us? All right, so both of these are some relation in holomorphic curve theory. So I've barely told you what the OC map is, so I won't tell you the proof of this, but this is some sort of annulus argument in holomorphic curve theory to see either of these. Okay? Once you have them, there's an interesting corollary which tells you that if you found smooth subcategories of your Fukaya category, you actually know quite a lot about OC maps. Okay, so the corollary is that one, if you have a subcategory of the Fukaya category is smooth, then OC restricted to that subcategory is injective. Why? Well, OC restricted to the subcategory is, remember, the Shklarov pairing on a smooth proper category is a perfect pairing on a finite dimensional vector space. Okay, so OC restricted to the Hochschild homology of A is an isometry of finite dimensional vector spaces. Okay, but isometries are injective. Okay. Similarly, if also you knew that phi restricted to A was invertible with inverse, phi inverse restricted to A. Okay, meaning either that phi preserves the category or A split generates. Okay, maybe I'll just say it's true if phi split generates. Sorry, if A split generates or phi preserves the category, but it's maybe true in more generality than that. If you knew that, then this phi twisted OC map is injective also. For the same reason.
Equivalent to saying that phi and then the inclusion into the whole thing is quasi-equivalence.
Sorry?
If you're saying phi restricted to A is invertible, equivalent to saying that phi and then inclusion into the whole thing is a quasi-equivalence?
No, I don't necessarily want that. It's not necessary. So, for instance, I mean, sometimes you have, just phi preserves this category. It's invertible and it preserves the category. Therefore, it's invertible when you sort of look at the. When I say phi restricted to A, I mean the bimodule of phi restricted to A. And that should be an invertible bimodule. But OK. How much time do I have? Something. 6 to 10 minutes in that range, I think. OK, so I'll state some applications of this. OK, so there are various automatic generation type statements you can write down. So here's a version of it for compact symplectic manifolds. Say you found a full subcategory of the Fukaya category. Which satisfies two conditions. First, it's smooth. So you understood something about its A-infinity algebra structure enough to prove it was smooth. That's some intrinsic condition to that algebra, not involving any new understanding of morphisms in your category. Okay. OK, maybe I should say it's a non-empty category, so it should have like at least one Lagrangian with non-vanishing Floer cohomology or something. So let's say you knew that the algebra was, this subcategory was smooth, and you need one more assumption if the first Chern class of x is not equal to 0, that A is cohomologically big enough, meaning the rank of 0th Hochschild cohomology of A is greater than or equal to the rank of 0th quantum cohomology of your manifold. Okay. Let me point out that we only need this condition when the first Chern class is not equal to 0, because when C1 equals 0, I'm assuming I'm working with the Fukaya category that's, everything is Z-graded. And that implies that the rank of QH0, well, that's just the rank of ordinary cohomology, as opposed to like H even or something, okay? Which is 1. Maybe I should have assumed X was connected. OK, then, oh yeah, so say A satisfies both of these conditions, then A split generates. The Fukaya category. Also, joint work with Peretz and Sheridan, or some, or compatibility, some compatibility with algebraic structures and open closed maps and so on, that were proven in various settings, imply that all open closed maps are isomorphisms. OK, so maybe I'll say OC and CO. OK, so I'm going to just make a couple remarks. So first of all, this is not the first automatic generation result. In the literature, Peretz and Sheridan have an automatic generation statement prove automatic generation when C1 equals 0 under homological mirror symmetry type hypotheses on A. So A is assumed to be equivalent to some generating subcategory of coherent sheaves on some mirror variety, which, by the way, imply A is smooth. The result I've stated, I think, was also announced by Fumihiko Sanda. So I wanted to mention that. And maybe I should say the key idea in the proof is to, it's very short, actually. You use Abu-Zaid's generation criterion. So if OC restricted to some subcategory hits 1, then the subcategory split generates. Okay, so we've known for a while that these open closed maps tell us about, give us generators for the category. Oops. And now what we got from smoothness and this compatibility implies that OC is injective. And both of these are finite dimensional vector spaces, so OC will hit 1 if there's a rank inequality. Okay? Yep. Okay. Well, there are some other applications to Landau-Ginzburg models and so on, but that involve twisted OC. But ask me about them over lunch. Thanks.